Good evening to everyone.
Good evening, sir.
Good evening, sir.
Okay. Screen share is not given. Kindly give the share screen. First control, please. Okay. So we have seen the introduction already. I have given you the introduction about this. Now, semiconductor, we'll see this covalent bond. Okay, what is this covalent bond? Now, as I have told you yesterday, that at the absolute zero temperature, that is generally it is considered minus 273.15 degrees centigrade. This is known as a absolute zero temperature. So at this, the semiconductor covalent bond. Okay, first semiconductor behaves like pure insulator. Is pure insulator. Why it is behave like pure insulator? Because the covalent bond of valence electrons are very strong. Very strong. If it is very strong, means there is no conduction electrons. Conduction electron. Or to remove the valence electrons from valence band to the conduction band, it will take much energy or electric field that will be required at this temperature. Okay. Now, what is this covalent bond and why it is going to behave like an insulator? So this is important to know, and why it is difficult to break this covalent bond. Okay, so that will be the topic, covalent bond. So basically covalent bond means it is a molecular bond or chemical bond that involves the sharing of electrons with neighbor atoms. Okay, so it is a molecular bond or chemical bond that involves sharing of electrons with the neighboring atoms. This is also known as a bonding pair. Bonding pair. Now, in this bonding pair, basically, it will be in the stable condition because no stable condition means it is non-reactive. It is not going to react. Non-reactive. Why? Because its valence electrons are fully balanced. Okay, due to the sharing of the electrons. So it becomes non-reactive. It is not required to make any reaction with any other atoms. Now, when they are going to make a bonding pairs, that is what it is known as a covalent bonding. Then they also in this bonding, semiconductor, they mean semiconductors or semiconductors form a crystalline lattice structure. Okay, so they are going to form like this structure. And when they are in this lattice structure or crystalline, same like a sugar cube, if you see the sugar cube, it is same. It will look like that. And they are going to remain stable. So covalent bond, just I will put it here, how it looks like about the silicon. So this is the covalent bond of silicon. Now we know that silicon, they are having the four valence electrons. Silicon is having the four valence electrons. Even the germanium, they are also having the four valence electrons. Like this silicon atom, it is going to share its electrons with the other neighboring silicons and it is completely, it will become stable. So this is known as a electrons which is shared and of a covalent bond. So this is known as a bonding. This is the covalent bonding. So it is going to make a bond. So in this one, if you see that this silicon, it is having its own four valence electrons. It is having four valence electrons. Okay. And it is taking nearby silicon. So it is making a bond with that one here. So this silicon will become stable. Here, same way, this silicon is also going to take. So likewise, all the neighboring atoms will make a bond, and that is known as a covalent bond, and that is generally it is shown with the two lines like this. So these all are the bonds they are making, and if you see this structure, this is known as a crystalline structure. Okay, so it looks like a crystalline structure. If you see the energy band of this one, of silicon, again I am putting that one here. So you can see this is the energy band for the silicon. So 1.1 eV, that is the valence band, conduction band, and secondary. Germanium, this is also having similar way. Now remember about their EV, electron volt, that is again important. 0.7 EV, that is the germanium which is having. And it is having 1.1 EV. So this is the covalent bond of the silicon, whereas this is the covalent bond of germanium. Now, how this covalent bond is broken? Let's see that one. Again, I am going to make same. Suppose this is the silicon and it is having, okay, it is having its or then it is taking a it is sharing with the four silicons of nearby atoms. Okay. So nearby atoms okay, I think one. I need to make some different way. Need to make it like this. Okay. Now this silicon, this is having these four valence electrons. Okay, this is the valence electrons. Then the nearby it is sharing, so this becomes a covalent bond. So it is going to become a covalent bond with this. If it is becoming a covalent bond, now suppose we are going to give a heat energy to this one. Okay, we are giving the heat energy. When the heat energy is given, what will happen that this covalent bond will be broken. Suppose this covalent bond is broken and this electron is ejected from the covalent bond from the valence band and it has gone to the conduction band. So this electrons is here now. This has become a free electrons. From where it is ejected here, it is going to make a hole. So this is known as a hole. So whenever a electron is going to be free from the valence band to the conduction band, a hole will be created in the valence band. In the valence band. Means free electrons that will be there in the conduction band, whereas the holes that will be there in the valence band. Always. Always. Hole is going to be in the valence band. Now, this happens due to the external energy. So, when an electron is ejected from valence band, a covalent bond is broken and a positive charge hole is left behind. If we see the energy band of this one, so we are having the valence electrons here. Now suppose this is the valence electrons and this is the conduction band and this is the valence band. So when the heat energy is given, say the heat energy, this is ejected and it has gone and it is become a free electrons, whereas here it is going to create a hole. It is going to create a hole. So this will be the energy band of same. Now this hole is keep on shifting. Again, remember this hole will be keep on shifting. How it is shifting? These electrons will come and it will acquire this position. Then it is going to create a hole here. These electrons will move and it will acquire here and it is going to create a hole here. So likewise, the electrons are moving to the nearby and it is going to create the hole. It is going to create the hole. So hole is going to be shifting continuously, or it will travel to the adjacent atom by acquiring an electron from that atom. Now just see here. It means that if this electrons is going to come here, it will acquire. So it is a different atom. Now from here, this electron will come here because it has become a hole. Now it will acquire this position. Now here is a hole. This will travel and here the hole will be there and this atom will be shifted here. So likewise, the hole is shifting continuously. It is random. I am showing here continuously in this counterclockwise direction, but it is not like that. Random also it will be happening. Okay. That means the hole, we can say here the hole, this hole can travel to an adjacent atom by acquiring an electron from that atom which involves breaking an existing covalent bond and reestablishing a covalent bond by filling up the hole. So hole will keep on shifting. So hole is shifting. Now here, two things we should know, and that is two or three things you should note it, important to note. One is conduction band, or we'll say conduction electrons are always found in conduction band and free to flow in it. It is free to flow in it. So this is one thing. Second, holes exist always in valence band and flow in it. Now how the hole is flowing? I have told you. So hole can travel, okay, by to the adjacent atom by acquiring the atom, okay, electrons from that. Conduction electrons move almost twice as fast as holes. Now, in semiconductor, it is only in semiconductor, not in the conductor. The current flows in semiconductor is due to flow of free electrons and holes. Okay, so this is the current which is going to flow in semiconductor. Remember, we are talking about the semiconductor. So in semiconductor, the current which is flowing, that is due to the flow of the free electrons and the holes. Free electrons and the holes. Now here, one more thing you should know. One is known as generation of carrier. Generation of carrier. So this will generate if valence band gets enough energy. In this case, valence electrons will eject and move to conduction band. Okay, so this is known as a generation of carrier. So already we have seen this one. The opposite also is true. The opposite, that is known as recombination of carriers. Recombination of carriers. So recombination means free and these free electrons and hole, they can again recombine. Once it is going to get recombined, the conduction electron will become again the valence electron. So there will be no conduction electrons and there will be no hole because it will acquire the conduction electron will fall to the hole and there will be no hole and there will be no conduction electrons or free electrons. So if we see that one, it is going to be like this. That suppose here we are having the valence band and this is the conduction band. And suppose there is say the valence electrons and here we have the hole. And here we are having a free electrons like this. And suppose this free electrons falls here. So if it is going to fall here, then it is going to acquire this one. So there will be, here it is not going to create any hole. In conduction band, hole will never be created. It will be always created in the valence band. So now here in this case, there will be no hole in valence band. And here there will be, means there will be loss of one electron. So we can say no electron in conduction band. Means there was a pair of the electron and hole. So if one electron is moving from here, so there will be no electron in the conduction band and there will be no hole in the valence band. Okay. Now we can show some more because I have seen three, so I can show one more hole here like this. Okay, I can show like this. So if they are recombining here, in that case, there will be there is going to be, or I think we can show like this. So this is known as a recombination. Recombination. In that case, there is going to be no electrons in the conduction band and no holes in the valence band. So this is known as a recombination of the carrier. Recombination of the carrier. Or we can say this one, the process by which free electrons and the holes get eliminated is called recombination of carrier. Recombination of the carrier. Okay. So that's it about the introduction part of it. Let's see about the type of semiconductor today. Okay, so we will see this one. Type of semiconductor. Now, in the original form means in the lab only we get this one. So in the lab, we are going to have the semiconductors. So this is two types. One is known as a pure semiconductor, or this is also known as a intrinsic semiconductor. Then next is impure or extrinsic semiconductor. Extrinsic semiconductor. Now, pure semiconductor, like we can say silicon or germanium. This is a pure semiconductor. And when in this pure semiconductor, if we are going to mix, okay, when we are going to mix impurity, it is going to become impure semiconductor. So this impurity, that mixing or adding of the impurity, okay, is known as doping. Okay, so in the semiconductor, silicon or germanium, if impurity is added, it becomes impure semiconductor. This adding, this process is known as doping. The impurity that is added is known as a doping agent. Doping agent. So these doping agents are two types. They are two types. One is pentavalent doping agent and second is trivalent doping agent. Why we choose this one? Because this is going to have 5 valence electrons and this is going to have a 3 valence electrons. So if I am going to add the P, this one, if suppose in the impure silicon, I take this one, I add this. Okay. In this case, it is going to become a semiconductor that is known as a N-type silicon semiconductor. Silicon semiconductor, but in short, we say N-type semiconductor. This is because of adding the pentavalent atom or doping agent. If we are going to add trivalent, then it is going to make the P-type silicon semiconductor or germanium semiconductor. So this is the trivalent. Now exactly what is happening in this? Let's see. Now in the pure silicon, because the silicon, okay, let's see first what is the pentavalent atoms. Pentavalent atoms like we have, for example, arsenic, antimony, phosphorus. They are known as a pentavalent atom. Trivalent atoms like gallium, indium, aluminium, boron, they are known as a trivalent atom. Now, the silicon or germanium, okay, I'll write here. So, N-type semiconductor, how it is made? N-type semiconductor. So N-type semiconductor, we take a silicon and suppose in that we are going to add, suppose we have a silicon and we are going to add the antimony. Antimony is ASB. Okay, so this is a silicon and this is the antimony. So the silicon, this is having the 4 valence electrons, whereas antimony, it is going to have the 5 valence electrons. So if the 5 valence electrons are there, 4 valence electrons will make a covalent bond with the 4 antimony. Now just see here, these 4 valence electrons will make covalent bond with 4 valence electrons of antimony, Sp. So one valence electron is left. And this left, so this will be free and it will go to the conduction electron. So this valence electrons which is left and which is having no role now, it will move to the conduction band. So this becomes a free electron. Now remember, these free electrons we are creating in this with the process of doping, with the process of doping, with the process of doping. So in this case, free electrons will be created, but hole is not being created. Okay, free electrons will be created by the process of doping, but no hole will be created. No hole will be created. Remember this. So here the hole is not being created, only the free electrons are being created. But if we are going to make this N-type semiconductor, so this after becoming the covalent bond, it becomes a, because in the conduction band we have the free electrons, and this mixture of silicon and Sb, if it is in the room temperature, if it is in the room temperature, then it is also having the free electrons plus free holes pair. Now this free electrons and free holes pair is due to the room temperature, external energy. So this is the free holes and free electron. This pair also will be created in the room temperature, whereas by doping only the free electrons will be created. So if you see these free electrons here, these free electrons plus these free electrons, this becomes majority free electrons, because this becomes a majority carrier. Majority carrier. Whereas only the hole, this free hole is there. Due to the pair, only the free hole is there, that's it. Okay, that will be equal to the free electrons due to the room temperature. So these free electrons, these free holes will be known as a minority carrier. Again, remember, this is created, this is the pair, electrons and holes pair. This is created because it is in the room temperature, and only the free electrons that is created due to the doping, with the process of doping. So if we are going to do the doping, in that case, no hole will be created. Hole is not going to be. And because it is having the negative charge carrier, because electron is free from here. So when the electron is free from here, okay, let me tell you one more thing that is very important. Because if you understand this, you are going to understand the next. And I am going to tell you about the diode. So here, this is the antimony, SB. One electron is free due to the doping process, and it is making a covalent bond with the neighboring silicon. So you can see it has a complete four pair of covalent bond. But one valence electrons, this is going to be free. So this free electrons is due to doping process. Because the electron has moved from here, this ASB is going to become a positive ion. Positive ion. This is a positive ion because electron is already moved from it. And wherever the electron is going, that becomes a negative charge. That area will become a negatively charged. And this will be positively charged or positive ion because this balance, this electron balance is no more same. So it becomes a positive ion and here it is going to become a negative charge. And due to this negative charge, it is known as a N-type silicon semiconductor. Because it is made of the silicon, it is known as a silicon semiconductor. Okay. Now next, P-type semiconductor. Similarly, same way, we are going to have the P-type semiconductor. Already we have seen like silicon and boron. If we take the silicon plus we take the boron, in this case, silicon, it is having the four valence electrons, whereas the boron, it is having the three valence electrons. So there will be the three covalent bond. And one atom, or sorry, one electron will not have pair. So if it is not having a pair, it creates the hole. So a hole is created. A hole is created. So this hole is created by doping process. By doping process. In this case, no free electron is created. Only the hole is created. Okay, so we can say only a hole is created and no free electrons is created. Is created. Then from where the free electron is coming? Yes. If this mixture of the silicon and boron, okay, we can say silicon boron mixture or semiconductor, if it is in the room temperature, then the valence electrons are going to acquire the energy and some of the electrons will move to the conduction band In that way, it is going to create the free electrons plus free hole pairs. It will be always in the pairs. So free electrons and free holes, this is going to be there. So by doping, we are creating hole, and again in the room temperature, free hole is there. So that's why these two free holes will make a majority carrier. So free holes will be majority carrier, and free electrons, this is going to be minority carrier. Minority carrier. And here the hole is created. That means it is going to accept the electron in it. And when it is going to accept the electron, when it is going to accept the electron, till the time it is not accepted, then nothing will happen. When it is going to accept the electron, okay, there will be no more hole. But when it is going to accept this one, so when boron accept a free electrons to its hole, this hole is created due to the covalent bond. Okay, so free electrons to its hole, then boron B will become, oh sorry, negative ion. It will become negative ion. It is a negative ion. Okay. Now generally, because there is a hole, so due to hole, it is going to have a positive charge, and that's why it is known as a p-type silicon semiconductor. P-type silicon semiconductor. That's it. Just take a break, 5-10 minutes, then we'll again start. Okay, next topic. Because next topic I am going to start is P and out. So I will be starting from here. Okay, P and out. Okay. So P-type, N-type semiconductor, if it is combined together, then it is going to make one component, and that is known as a semiconductor diode. So this is known as P-N diode. This side it is going to be anode, whereas this side it is going to be cathode. The symbol is it will be written A, it is going to be K. Now, how we are making this one? Or when we are going to make, what is happening? First of all, what we do, that we are taking a single piece of Si or germanium semiconductor. This is also known as a substrate or a bar, we can say bar of silicon and germanium. So if we are going to take this bar, suppose we have taken a bar of the silicon, and half of this is doped by the trivalent impurity. So it becomes P-type semiconductor here. And pentavalent impurity, it is going to make the N-type semiconductor. So if you are going to make like this semiconductor, the contact surface of P and N semiconductor is known as a P-N junction. So this is a contact surface. Contact surface of P and N type semiconductor is known as P-N junction. So this is the junction. Now this side we are going to have the hole. So this hole are going to be in the majority carriers. And this side we are going to have the electrons. This is the free electrons. So these free electrons they're the free electrons. And there will be the minority carrier here also, and here also we have the minority carrier. So the contact surface is going to be PN type semiconductor. Okay. Now as soon as the contact surface has formed,
திரும்பி class.
Thereafter, the electron is going to move from here. It will cross this junction and it is going to fall on the holes like this. So these electrons will move and it will fall on the holes. If it is going to fall, then this is known as a recombination. Already I have told you what is the recombination. Recombination of carriers. So if the recombination of carriers will be there, so there will be no electron and no hole. So this area is going to be depleted due to the recombination of the carriers, and there is going to be no hole and no free electrons. So this area is known as a depleted area or depletion region. Depletion region. Then what is going to remain? So there is going to be, because the electron has moved from here to here in the hole. So the pentavalent atom will become a positive ion. So here only the positive ion that is going to remain here because it has lost one electron. And the boron that has accepted the ion, so this side it is going to have the, it has accepted one electron, so it is going to be negative charge. So positive charge will develop here and negative charge is going to develop here. This recombination will be continue till the time this charge which is going to develop across the junction is going to repel the further movement of the electron. If it is going to repel the further movement of the electron, this is known as a barrier voltage or barrier potential. Barrier means it will not allow now the electron to cross the junction. So this is going to develop a potential and that is known as a barrier potential. Till the time barrier potential is not developed, the electron will continue to move and diffuse. This will be continued. Okay. And after the barrier potential is developed, this diffusion or recombination will stop. So this thing is going to happen as soon as the PN junction is developed, and thereafter the recombination of the carrier will start. When the recombination of the carrier started, the depletion region will develop, and in that the positive ion and negative ion will remain there. So it is going to have a positive charge in the N-type region and negative charge in the P-type region. So this will develop a potential across the p-n junction. Now, this recombination of the electron and hole will be continued till the time this potential which is going to develop is sufficient enough to repel this electron. When it is repelling the electron and electron is not able to cross now, this potential is known as a barrier potential. This potential is known as a barrier potential. So if it is made of the silicon, remember, if it is made of the silicon, this barrier potential, that is the V naught, is going to be 0.7 volt. And if it is made of the germanium, then V naught is going to be 0.3 volt. 0.3 volt. So just see here what is happened, and there is, till the time this diffusion takes place, there is going to be a current that is going to flow, and that current is known as a diffusion current. That current is known as a diffusion current. So you can see here, this is the N-type region. Here we have the P-type region. This is the pentavalent atom. When the electron has moved, it is going to diffuse, so only the positive ion and negative ion is going to remain. So it is going to develop a depletion layer. So voltage is going to develop across this, and this voltage is known as a barrier potential. Till the time diffusion is going to take place, the current is going to flow in the circuit, means current will be flowing, and that is known as a diffusion current. That is known as a diffusion current. Okay. So what so far we have understood in this, so let me write this one little bit. Okay. So we can say here this one, just I will be writing very short, small notes, short notes, that electrons from N region diffuse to P region near PN junction, near PN junctions. So it develops the depletion layer. The positive ion and negative ion. No, positive ion in N region. Positive ion in N region and negative ion in P region will develop a potential across PN junction. Okay. The diffusion is continue till the potential repels the electrons of N region. So this potential is known as barrier potential. Barrier potential. Okay, so this much is more than sufficient. What is barrier potential? Now let's see the energy band of this. The energy band, let's see about this one, how it looks like. Now you can see this is the p-type semiconductor and this is the n-type semiconductor. And here, as soon as the p-n junction, this is the p-n junction formed, p-n junction is formed, the electrons of the n-type conduction band is falling to the p-type semiconductor holes and they are going to deplete. Deplete means there will be no hole and there will be no free electrons. So in that case, it is going to develop a charge across this. And this charge here, it is going to be a positive charge and this side negative charge. And there is going to be the depletion. Because it is being depleted, this region is being depleted of the carrier. So that's why it is known as a depletion layer. But when the depletion layer is formed, the charge is also going to be formed. So this side it is going to be positive charge and this side it is negative charge. And when this charge is going to be for the silicon 0.7 volt and for the germanium it is 0.3 volt, the diffusion stops. This is going to stop. So this voltage is known as a barrier potential. Barrier potential. So this voltage is known as a barrier potential. When the barrier potential is developed, there is further diffusion of the electrons to the with the hole stops. Okay, it is going to stop. So this is about the PN junction. Now let's see about the biasing of the PN junction. Biasing. So we have the PN diode here. So suppose this is the PN diode. And this is the, okay, I'll not make here because there is a depletion region. So here we have a depletion region. Then here we are going to have the whole majority carrier is the whole, and here so this is the P type semiconductor, this is the N, this is the junction, PN junction, and this is the depletion layer, and here this is the barrier potential. When we are going to connect with the battery, so suppose if we are going to connect with the battery, when the P is connected with the positive terminal of the battery and N is connected with the negative terminal of the battery, this is known as forward biasing. This is known as a forward bias. Forward, forward bias. So here the negative is connected to the N, positive is connected to the P. Now when it is connected like this, the the electrons, now let's draw this one by one like this. These electrons will move towards the junction. It is going to move towards the junction like this. This will move towards the junction. And when it is going to move towards the junctions, the electrons from here, it is going to move and it is going to arrive to the N-type region and it will acquire these places like this. Okay, so it will try to push this one. Same way, this positive here is connected, the holes that will be again pushed or repelled by the positive terminal towards the junction. This is also going to move towards the junction. And because it is going to move towards the junction, the depletion layer narrows down. This will be happen till the time the voltage here, the applied voltage, that is the V, is less than the barrier potential voltage, that is the V naught. This will happen till V applied voltage is less than the barrier potential voltage. V naught is barrier potential voltage. When it is going to become equal, when the V is going to become equal V naught, that time these electrons, because it will narrow down, this will get narrows down here. It will be further, it is going to narrow down like this. So this will be the depletion region now. And these electrons will be able to move this one. This will be able to cross, it will come here to these electrons. Okay. This is coming here. Then this is going to move here. And this is going to move here. Again, this is going to move here. And it will be out because in the conductor, only the electrons that is going to flow, no holes is going to flow. Inside the semiconductor, holes flow. But in the conductor, only the electron that is going to flow. And likewise, electron flow will be completed. So the current starts flowing in the circuit. So this is the current that is going to flow. And this is the conventional current that is going to flow. So this is what is going to happen in case of the forward biasing. So this will happen in case of the forward biasing. Okay. Hope you understood.
Yes, sir.
Okay. Now let's see about the reverse biasing. Reverse biasing, what is happening in that? Okay, again I am making same. There is a majority carrier, that is the hole, and there are the minority carriers in this. This is the P-type semiconductor. Here we have the N-type semiconductor. And here we have the hole. When the battery supply is connected to P is with the negative terminal of the battery, and when the positive is connected to N semiconductor, this is known as a reverse biasing. Okay, this is known as a reverse biasing. Now in the reverse biasing here, the negative terminal is going to attract the hole. Hole is going to be attracted towards the negative terminal, like this. So if it is being attracted here, in this case, okay, let me make this also this side, because this is going to be attracted towards the positive terminal, like this. So these electrons from here, these electrons will move and these electrons will flow to the positive of the battery. It will flow to the positive of the battery. And these electrons will reach like this. And these electrons through the holes, they will move from here and it will reach here. And again, they are going to recombine here. So once they are going to recombine, means suppose I have applied a voltage V1. So at the V1, this is the depletion. This is going to deplete like this. So this electrons which has moved, now it is going to have here the negative ions, and this side it is going to have the, sorry, this side positive ions and this side negative ions. So this is going to increase the depletion region. So this is going to increase the depletion region. So here we are going to have the increase the depletion region when we are going to increase the voltage. Okay, so suppose at the V2, at the V3, like when the V1 is there, this is the depletion region. That is what I am showing with the ions like this. And in case of the V2, suppose this is the ions or depletion, and suppose with the V3. So as the voltage is going to be increased, depletion region is going to increase. Temporarily, the flow of the electron will be there and thereafter it is going to stop. Okay, so this will be temporarily till the time these electrons that is going to come here. It is not crossing the junction. Remember here, these electrons are not crossing the junction. It is simply, it is moving towards this side and again it is going to reach and deplete the holes. So the depletion region is going to become widened. White. White depletion region all layer. So depletion layer is going to increase. So this results in a widening of the depletion region and a depletion of the majority carrier. Majority carrier is going to deplete. So as the reverse voltage is increased, as the reverse voltage is increased, the depletion region is widening and majority carriers are depleted. So as we are going to increase, same thing is going to happen. It will widen and majority carrier will deplete. Then it becomes steady. Again, we are going to increase the voltage. Again, the sum of the carriers is going to get depleted. So like that, depletion region is keep on increasing. As the voltage is going to be increased, it will increase. Now, This barrier, this is also going to develop the barrier potential VO. So VO1, we can say VO2 or VO3. Now when V01 becomes equal to the V1, the flow of the electrons stops. Similarly, when the V02 is the barrier potential when the V2 voltage has been increased. When the barrier potential is going to become equal to the V2, this is the applied voltage, this is the barrier potential, then the flow of the electrons will stop. But by the time your depletion region, this is increased. When we are going to have the V03 is equal to V3, this will happen if we are going to increase the voltage here, depletion region is going to increase, and when the barrier potential becomes equal to this, it is going to stop. Again, electron flow is going to stop. Now, remember, in this, we are having the minority carrier also. So here, this is the minority carrier. This is also a minority carrier. So minority carrier in N type and P type, these minority carriers are basically a forward bias to them. When majority carrier are reverse bias the majority carrier, the minority carrier are forward bias. They are forward bias. So if they are forward bias, that means they will start flowing. So they can easily, this is having a forward bias, and whatever the voltage is there, due to that it is sufficient to cross this one here, and through the electrons it will be start moving. Okay, so these free electrons will move this side and it will cross. Only this is going to cross. Free electrons, this one is cross. So if it is going to cross, that means a very small current in the microampere, this current will flow. Microampere, this will flow, and this is known as a reverse saturation current. Reverse saturation current. And this reverse saturation current is due to minority carrier forward bias. Minority carrier. It is due to the minority carrier. Now, if we are going to increase, okay, but how this is easily it is going to cross? How this is able to cross this one? If you have seen here, I have shown you something in this one. This one. Can you see here? Here. So here the minority carrier which is there, that is in the P type, we have the minority carrier. They are able to fall to the and becomes a valence band here. Here. So they are going to be a minority carrier, and they are going to fall. So here whatever, like suppose we are having a minority carrier, that is the electrons here. And here we are going to have the hole. Hole will be always in the valence band. So this minority carrier is easily it is going to fall here. Okay, it is going to Uh, so it is going to fall here. It is going to fall like this. Due to the this is known as a energy hill. And because this is the higher side of the hill and this is the valley, so it will be easy to fall from here to here when the potential is applied. So that potential, a small potential if it is applied, this is easy to fall from this magnetic carrier from here to here. That is the same thing we are saying here in this case. So although the depletion region is very large, but because it is the higher side of the energy and this side is the lower side of the energy, it will be easy to fall. And that's why it is able to cross. Okay, this is able to cross and small energy, whatever the energy we have given, that is more than sufficient. Now, problem is not here. Problem is if the reverse voltage is increased continuously, the kinetic energy of electrons, that is the minority carrier, become high enough. High enough. This is we are talking about the minority carrier. So what happened? They speed through P region they collide and knock out valence electrons from covalent bond and liberate new free electrons to conduction band. This will happen. Now this new liberated conduction electrons, again because this new free electrons also have high energy, high kinetic energy, because they are also going to have the high energy, they also repeat the same process. Same process, what the process above we have seen, same process they are also going to repeat. If all are going to repeat same process, what will happen? In a quick time, in a quick time, the number of new free electrons liberation or liberated new free electrons increases. In a quick time, it is going to increase. Now, because these free electrons increases and they have a kinetic energy, so when they pass through depletion region, they pass through the depletion region and now they are not combining with the whole. They are just passing, rushing through that and increase the temperature of junction. They are going to increase the temperature of the junction. Okay. The multiplication of conduction electrons as discussed above is known as the avalanche effect. Avalanche effect. It is known as a avalanche effect. Now, when the depletion region, when they are going to rush through, the temperature is going to increase. Then what will happen? A sudden rise of reverse current and sudden fall of resistance of barrier region. Now, due to this, the PN junctions breaks down. Breaks down. And when it is going to break down, a reverse voltage at which PN, okay, breaks down permanently. Permanently. So at which a reverse voltage which PN junctions breaks down is known as reverse breakdown voltage. Reverse breakdown voltage. So this is known as a reverse breakdown voltage. Okay. And this reverse breakdown is also known as a avalanche breakdown. And this reverse breakdown is also known as avalanche breakdown. Okay, this is also known as a avalanche breakdown. That means your diode has been damaged. It is completely damaged. Any doubt to anyone up to here?
No, sir.
So let's see the VI characteristics of this. So this is the VI characteristics of the diode here. So if it is made of the silicon, there is the silicon semiconductor. In that case, 0.7 volt is barrier potential. And after the 0.7, it is a forward bias conducting. So forward current is going to increase. Till that, it will be in the blocking state. When we are going to give the reverse one, then the small current is going to flow in the reverse direction. So this is known as a reverse saturation current. Due to minority carrier. It is due to the minority carrier. When it is going to reach to the breakdown voltage, reverse breakdown voltage, suddenly the current is going to rise. So this is the sudden current will rise. And this sudden current will rise due to resistivity of junction is broken down due to avalanche effect of electrons, minority electrons. So due to the avalanche effect, it is already broken. The temperature of junction rises and it damages permanently. Permanently. Okay, so this is what it is going to happen. And the diode is completely damaged. Okay, it is something like a short circuit. It is damaged. So this is the voltage current characteristics of the diode in the forward biasing and reverse biasing what happens. Okay, so that's it for today. Any doubt to anyone up to here? Thank you very much and good night to everyone.